So in the session before this, we saw universities realizing that they're being asked by their funders to commit to store data for the long term, and working out that this requires a substantial financial commitment, and starting to ask how much are we talking about. And this is part of an ongoing research program. This paper describes joint work with my colleague Daniel Vargas, and it relies on modeling work that I'm doing with Daniel Rosenthal, who's no relation, Ethan Miller and Ian Adams at UC Santa Cruz, Eric Zadok at Stony Brook, and Mark Storer of NetApp. The paper examines the question of whether the use of cloud storage can reduce the cost of long-term digital preservation, and reports on an experiment in which we ran a lockbox in Amazon's cloud and recorded detailed costings and compared them with local costs. Normally this talk would be about the experiment, but actually a lot has happened in cloud storage since we did the experiment and submitted the paper and everything. And although these developments don't really change our conclusions, I'm sure that the recent developments are more interesting to the audience than the stuff they can go and look up in the paper. So I'm going to cover the motivation for our work, briefly discuss the experiment, and then focus on recent developments. As usual, I hope to say something that people will disagree with, so I'll try to leave plenty of time for questions. So money turns out to be the major problem facing the future of our digital heritage. Broadly speaking, the extensive research on the cost of preservation concludes that, looking back, about half the money to preserve an object is spent just simply ingesting it, and about a third storing it, and about a sixth disseminating it. So if storage has only been about a third of the cost, why are we worrying about it? And the answer lies in this graph, which illustrates Kreider's law. Kreider's law is the analog of Moore's law of the disk, and actually it's even faster than Moore's law. And there's a 30-year history of disk prices dropping about 40% a year. Figures from the San Diego Supercomputer Center show that media is about a third of the total storage cost, the rest being power, cooling, space, staff, software licenses, all this other stuff. But all these other costs are pretty much per drive rather than per byte, so that the total per byte cost drops roughly in line with media costs, and this means that customers get roughly double the capacity for the same price every 2 years. Thus, the cost of storing a digital object rapidly becomes negligible. The perception was that if you could afford to store it for a few years, you could afford to store it forever. Kreider's law has held for 3 decades. Surely it's good for another decade or 2. Well, here's XKCD's explanation. It's really always tempting to think that exponential curves will continue forever. But in the real world, they're always just the steep part of an S-curve. So here's a graph from Dave Anderson of Seagate from 2009, I think, no, 2008, which shows how what looks like a smooth Kreider's law curve is actually the superimposition of a series of S-curves, one for each disk drive technology. And notice how Dave's graph shows perpendicular magnetic recording, PMR, which is the current technology, being replaced by heat-assisted magnetic recording, HAMR, starting in 2009. Well, no one has ever shipped a HAMR drive. If we'd stayed on the Kreider's law curve, we would have had 4 terabyte, 3.5-inch SATA drives in 2010, early 2010. Instead, in late 2012, the very, very first 4 terabyte drives are just hitting the market. So it was clear by mid-2011 that the industry had fallen off the Kreider curve. That was before the floods in Thailand destroyed 40% of the world's entire capacity to build disk drives. Disk drive prices doubled almost overnight. Prices are not expected to return to pre-flood levels until 2014. By then, they should have been 50% lower. The latest industry projections are for no more than 20% a year over the next 5 years. There are many reasons why even this may be optimistic, such as industry consolidation and the shift from a 3.5-inch to a 2.5-inch form factor. So Bill McKibben had this wonderful article in Rolling Stone called Global Warming's Terrifying New Math. He uses 3 numbers to illustrate the looming crisis. So here are 3 numbers that illustrate the looming crisis in long-term storage. According to IDC, the demand for storage each year grows about 60%. According to IHS iSupply, the bit density on the platters of disk drives will grow no more than 20% a year for the next 5 years. Now, the bit density doesn't exactly map to the prices, but they're very closely related. And according to computereconomics.com, IT budgets in recent years have grown between 0% a year and 2% a year. So here's a graph that projects these 3 numbers out for the next 10 years. The red line going down is Kreider's law at IHS iSupply's 20%. The blue line, which is pretty much flat, is the IT budget. And the green line is the annual cost of storing the data accumulated since year 0 at the 60% growth rate projected by IDC, all relative to the first year. So 10 years from now, storing all the accumulated data will cost over 20 times as much as it does this year. So if storage is 5% of your budget this year, in 10 years it will be more than 100% of your budget. If you're in the digital preservation business, storage is already way more than 5% of your IT budget. So we need to focus on this triangle between the blue and green lines. We need some combination of an increase in the IT budget growth rate by an order of magnitude, a radical reduction in the rate at which we store the data, or a radical reduction in the cost of storage media. Many people believe that there's a fourth alternative because there's some magic in quotes, the cloud, unquote, that makes storage much cheaper. I've spent the last year looking at the numbers behind this affordable cloud storage hype. We ran a LOCKSS, collected detailed cost numbers, looked at the pricing history of cloud storage, and I used our prototype economic model to compare cloud and local storage costs. So here's the experiment. The detailed numbers are in the paper. We collected these numbers, we scaled them up to match the median box in the global network of LOCKSS boxes, and then projected the numbers out for 3 years to compute a 3-year total cost of ownership. Depending on the exact assumptions we used to make these projections, the projected 3-year total cost of ownership ranged from the A case, which was $11.6K, to the B case, which was 19.1. We would expect in practice costs closer to the A case. The hardware cost of the median box in the global LOCKSS network with the B assumptions is less than 1.5K. So even if we compare it to the cloud box with the A assumptions, running costs would need to be over $280 a month to make local LOCKSS box more expensive than running a LOCKSS box in Amazon's cloud. Now, $280 a month is enormously higher than people incur in practice running LOCKSS boxes. So the conclusion that local storage is cheaper than S3 is supported by our modeling work, which I'll now go on to describe. We model a chunk of data through time as it migrates from one generation of storage media to another, hopefully taking up less and less of the storage medium each time. The goal is to compute the endowment, the capital needed to fund the chunk's preservation for, in our case, 100 years. The price per byte of each media generation is set by a Kreider's law parameter. Each technology also has running costs and costs for moving into that technology and then moving out of it to its successor. And interest rates are set each year using a model based on the last 20-year history of inflation-protected US treasuries. I should add the caveat that this is still a prototype, so the numbers haven't actually been validated against real data. That's actually a difficult thing to do. but the shapes of the graphs and the relative costs of different things look very plausible. So in order to make a comparison, we need a baseline local storage cost model to compare with the cloud cost. It should lean over backwards to be fair to cloud storage. I don't know a lot of good data to base this on, but I use numbers from Backblaze, which is a PC backup service. They publish detailed build and ownership costs for their 4U 117 terabyte storage pods. I took their 2011 build cost and increased it to reflect the then 60% increase in disk costs since the Thai floods. Based on numbers from San Diego and Google, I added running costs so that the hardware cost is only 1/3 of the total 3-year cost of ownership. Note that this is a lot more expensive than the numbers that Backblaze publish. I added move-in and move-out costs of 20% of the public purchase price for each generation of media. And then I multiplied that total by 3 to reflect 3 geographically separate replicas of the data. The result is this graph, plotting the endowment needed to have a 98% chance of not running out of money in 100 years against the Kreider rate. In the past, with Kreider rates in 30 to 40% range, we were over here in the flat part of the graph. Where the precise Kreider rate isn't that important in predicting the long-term cost. As Kreider rates decrease, we move into the steep part of the graph, which has 2 effects. The cost increases sharply, and the cost becomes much harder to predict because it depends strongly on the precise Kreider rate, which we're not going to know because it's in the future. Now, we do the same thing for S3, setting the purchase cost to 0 and the running cost from S3's published prices. The only additional cost is the running cost of one Amazon virtual machine to do the integrity checking. So the result is this graph showing that S3 is not competitive with local storage at any Kreider rate. This comparison is misleading because it assumes that local storage and S3 encounter the same Kreider rate. So here's a table showing the history of the prices for several major cloud storage services since their launch. The Kreider rates are 10% or below, except for Google, which made a major pricing mistake when they introduced their service at the end of 2011. They thought that they could price their service significantly higher than Amazon's and get any business at all. They were wrong. So, if local storage matches IHS's projected 20%, you get this point on the green line. And if S3's matches their historic 7%, you get this point on the red line. The endowment needed in S3 is more than 5 times larger than in local storage, and it depends much more strongly on the Kreider rate. So this graph raises 2 obvious questions. First, why isn't cloud storage getting cheaper? Why doesn't Amazon drop S3's price as the cost of their underlying storage drops? And the answer is they don't need to. Their customers are locked in by bandwidth charges, and they have the bulk of the market at their current prices. And the estimates are that Amazon has about 90% of the cloud storage market. Their competitors match or even exceed their prices. Why on earth would Amazon bother to drop the prices? They're making boatloads of money. And why is it so expensive? After all, even using S3's reduced redundancy storage to store 117 terabytes, you would pay in the first month almost enough to buy the hardware for one of Backblaze's storage cards. So the answer is that for the majority of S3's customers, it's actually not that expensive. 2 reasons. First, the customers aren't in the business of storing the data for the long haul. Their data has a much shorter shelf life than the life of the drives, so they can't amortize the cost across the full life of the media. And secondly, their demand for storage has spikes, goes up and down. By using S3, they avoid paying for the over-provisioning to cover the spikes. Long-term storage has neither of these characteristics, and this makes S3's business model inappropriate for long-term storage. Amazon recently admitted this when they introduced Glacier, a product aimed specifically at long-term storage with headline pricing between 5 and 12 times cheaper than S3's. Now, doing this, they had to make sure that Glacier did not compete with S3 and cut into the boatloads of money that they're making. So they gave it two distinguishing characteristics. First, there's an unpredictable delay between requesting data and getting it. Amazon says that this will average about 4 hours, but they don't commit to either an average or a maximum time. Secondly, the pricing for access to data is designed to strongly discourage accessing it. There's a significant per-request charge to motivate accessing it in large chunks. And although you're allowed to access 5% of your data each month with a no per byte charge, the details are very complex and hard to model. Now, as I understand it, if on any day in a month you exceed the prorated free allowance, i.e. about 0.17%, depending on which month it is, you're charged for the whole month as if you had sustained your peak hourly rate in that month for the entire month. So you want to be really careful accessing it. In order to model Glacier, I had to make some fairly heroic assumptions. No accesses to the content other than from integrity checks. Accesses to the content for integrity checks at precisely uniform rate. Each request for 1 gigabyte of content. And we get this graph, which shows Glacier with no integrity checks, with checks every 20 months, checks every 4 months, and for comparison, S3, which is the red line, and local storage is the green line. It looks as though Glacier with 20 months checks is slightly cheaper than local storage, and with 4 month checks is more expensive if the cryo rates match. But the thing you know about Glacier is it's at 1 cent a gigabyte a month. This is a great price point. They are not going to move that down for a long time. But even this is not an apples-to-apples comparison. Both local storage and S3 provide adequate access to the data. Glacier's long latency and severe penalties for unplanned access mean that, except for truly dark archives, it isn't feasible to use Glacier as the only repository. Even dark archives, Glacier's access charges provide a very powerful lock-in. Getting data out of Glacier to move it to a competitor in any reasonable time frame would be very expensive, easily as much as a year's storage. So, providing adequate access requires maintaining at least 1 copy outside Glacier. If we maintain 1 copy in Glacier with 20-month integrity checks, a 7% cryo rate, 1 copy in local storage at a 20% cryo rate instead of 3 in our earlier examples, the endowment needed would be 517K. The endowment needed for 3 copies in local storage would be 486K. So it's about a wash. Replacing 2 copies in local storage with 1 copy in Glacier has little effect on the cost. Its effect on robustness would be mixed. You get 4 copies instead of 3, and greater system diversity, both of which are good, but less frequent integrity checks, which is bad. So here's the conclusions. Commercial cloud storage services like S3 are simply too expensive to be used for digital preservation, and the reasons are not technical, they're business reasons. And so they're unlikely to go away. Access and lock-in considerations mean that it's very difficult for a digital preservation system to use Glacier as its only repository. Even with generous assumptions, it isn't clear that using Glacier to replace all but 1 local store reduces cost or enhances overall reliability. And if you do go this route, you're going to have to manage accesses to the Glacier copy very carefully if you're not to run up unexpected huge access costs. So I'll leave you with this thought experiment. Suppose we decided to keep everything in S3 forever. So just to emphasize, everything I've been talking about is about commercial cloud storage services. This isn't to say that a private cloud storage service would not be a good economic bet, but in order to do that, you have to organize your private cloud storage service so that its pricing follows the media down the private curve. That's the most important consideration. Not the current price, but how rapidly it drops over the long haul, because the evidence is that commercial cloud storage services, for business reasons, do not follow that curve. Okay, I hope I said something to disagree with you.